Hi, my name is Ryan, and the entire purpose of my channel is to help you pass the FE mechanical exam. Today, we're going to be going through the solution to this problem. We're going to be using the official FE reference manual and just solving this problem step by step. The first link in the description below will allow you to try this problem for yourself interactively for free, as well as every other problem that I've solved in my FE exam playlist. So I highly recommend you go ahead and solve those problems. Let me know in the comment section below how you did. I read every single one of the comments, and I'll definitely reply to your comment. I hope you want to try to solve the problem. Let's get into the solution now. It says a collar is pin connected to a rigid link ABC and slides vertically downward along a smooth, frictionless guide with a constant speed of 600 millimeters per second. A lot of information there. It says the geometry of the system is shown in the figure above. At the instant shown, point D is pinned to a fixed location. Determine the angular acceleration of the link ABC at this instant. And it looks like we're looking for the magnitude and direction. Let's transfer this to a clean sheet of paper here. Let's just write down some of the things that we know before we think about a solution here. Now it says the collar is moving with a speed. The collar is point A, essentially. It's moving with a speed downward of 600 millimeters per second. And you see, one of the things that I did here was I have a set of unit vectors that I'm working with, the regular Cartesian basis. It's moving 600 millimeters per second downward, so that'll be in the minus j direction. And if it's moving with a constant speed, which it says right here, that means that the acceleration of that point, acceleration of point A, must be equal to 0, right? The time derivative of the speed is equal to the acceleration. The derivative of a constant is 0, so the acceleration of point A is 0. Okay, it doesn't look like we're given any other information. There's some geometry in the schematic. How could we solve this problem? Now you look at this problem, you see multiple different rigid bodies connected to each other. They're moving relative to each other. It might give you a hint that you're going to have to use the rigid body relative motion equations. So let's check and see in the manual where we can find that. Now this is in the dynamic section here, under the section relative motion. And what we're looking for is the angular acceleration of that link. I think this would be the right equation that we use. Let's start with this equation and see how we can further break down the problem to think about the knowns and unknowns that we have and what we need to do to solve for this angular acceleration. Now you can see there's 2 points here in this equation, points A and point B. Those are points that we select that belong to the same rigid body. So if we go back here and think, we have multiple different points that we can pick. We can either pick point C or point B. If we think about some of the things that we know in terms of point C isn't moving with any kind of simplified motion, right? It's it belongs to the same body as point A, so it's a valid point, but it doesn't have any kind of simplified motion, right? We don't know anything about how that body is going to be moving. It's moving with a circular motion combined with this kind of translation, so it's a complex motion. What about point B? Point B is a point that we can work with. Why? Because it's pin connected here. It belongs to another body, dB. So it's constrained to move on a circular motion path of radius 80 millimeters. For these problems, one thing that's super important is to be able to recognize points that move with circular motion because we understand circular motion very well. So what we're going to do is quickly review circular motion. If you understand circular motion, these problems become very simple. I put together a slide here. This reference here is from the dynamic section where it talks about plane circular motion. And I have the page number there, 103. Now, firstly, let's say this is our linkage that we previously had. This is our linkage dB. Now, dB, this would be like point D here, and this is point B here. It's moving with a radius equal to rho, let's call it r here. If you have that link moving with a angular velocity omega, the link moving with a angular velocity omega will produce a speed at the end, which is equal to r omega. And what about if it's accelerating, if it also has an alpha? If we're talking about accelerations, it'll move both with a tangential component and a centripetal component. The centripetal component we can write as r omega squared, or using the definition of the speed r omega, if we plug it right in here, we can get this relation, v squared over r. So we have a centripetal component, we also have a tangential component, and r alpha pointing in the tangent direction. So now that we understand circular motion, we can fully break down the motion of that point B. Another point I would like to hit on is if we look at that relative acceleration equation, there's a double cross product term here. Now we really want to avoid these double cross products on the FE exam. We could use the calculator to perform a double cross product, but again, it's just going to take more time. One thing that I want you guys to remember is for 2D planar dynamics problems, omega is always perpendicular to the relative position vector. Omega, from the right-hand rule, if it's clockwise or counterclockwise, your thumb points in the direction of omega. So if we're counterclockwise or clockwise, it's always going to be pointing in the k direction out of the page. And the relative position vector is always in the plane of the screen. So that means their dot product will always be 0. I took this reference here from the mathematics section. Now this is just a kind of proof here, but if you look at a term here, which is, this is the curl of a vector, written in terms of the gradient operator, but it's also applicable to any double cross product that we have. For instance, you could see these terms in the red boxes here look very similar. They both are double cross product, and they both have the same vector crossing first. If we kind of write that in a similar format, we get this. And you could see that because omega is perpendicular to the relative position vector, this term will always be 0. So we'd be left with a very simplified equation here, which is just omega squared pointing in the RA relative to B, and that's a negative. So what we're going to do here is we're going to work with this equation on the bottom. And you can always work with this equation. You're not going to have any three-dimensional dynamics problem on the FE exam, and avoiding that double cross product is going to help you save time. Okay, now that we've addressed some of those important points, let's go ahead and plug into our relative motion equation. Okay, now that I've written down some of these important terms here, firstly, we know that the acceleration of A was 0 because that point A was moving with a constant speed. The acceleration of B is moving with a circular motion, right? If we draw out those vectors here, it's moving in the tangential direction here with a tangential acceleration equal to r alpha. And then it's moving with a centripetal component as well, because that link could have an angular velocity, which it will. Moving with a centripetal component equal to the speed at B squared over the radius of BD. Okay, so we understand the motion of AB, but we have no idea what the angular acceleration or the speed at point B is. That's two unknowns. We don't know the magnitude and we don't know the direction of the acceleration at B. Now, for the angular acceleration of AB, we're not sure what the magnitude is. That's what we're looking for in the problem, but we know its direction. It's either going to be pointing into or out of the page. We know the relative position vector of A relative to B. That's this kind of vector here. Or A relative to B. And omega AB, we're still not sure about. So we have multiple unknowns, and we have a two-dimensional vector equation here. What that means is that we're going to be able to project it in two directions and have two equations, but we still have four unknowns if you count the question marks. Let's go ahead and solve for that angular acceleration of a, b, and c. What's left to find? I'm going to plug into this equation everything that we just said, and then I'm going to come right back. Okay, I went ahead and filled out the entire equation. Now I'm just going to perform this cross product. This cross product is really simple here. If you just remember this kind of uh, cross product trick here. If we have a rigid triad, this ijk here, all we know is that I cross j is k cross I is j, and j cross k is I, if you just follow that circle. So that k we can distribute to the I and distribute to the j. That's equal to negative 120 alpha AB, and we know that k cross I is just j. And then here we know that k cross j is just going to be negative I. So we end up with negative 50 alpha AB pointing in the I direction. And I'm going to just fill in the rest of the equation. There's no more cross product to do. So I'll come right back. Okay, now that we have the full acceleration equation, if we think about what direction could we look at in order to get the things that we care about most easily, what we care about is alpha AB. So I'm thinking that the x direction equation is not going to help us a lot. Why? Because it has this alpha BD term. That's the alpha of this linkage here. We don't really care about the x direction alpha BD. So let's ignore that, and let's mathematically what we're going to do is dot both sides of this equation with j hats. Or we can look at all the j components, which is exactly the same thing. So I'm going to write down the j component equation. This is the j equation. If we go ahead and solve for alpha, what we get is VB squared divided by RBD minus 50 omega AB squared. Take this entire thing and divide by a 120. All we need to do in order to solve this problem is to be able to find this speed of B and omega AB. And we'd be able to find those quantities if we use the relative velocity equation. So let's go ahead and write down the relative velocity equation, which is this equation. Okay, if we think about some of these terms here, the speed of A was given. The speed of A is 600 pointing in the minus j hat direction. What about the speed of B? Remember that speed of B, that point B is moving with a circular motion, is going to be moving towards the right hand side. We could just mark that though as the speed of B pointing in the I direction, right? And why did I choose not to break it down into its circular motion is because you can see we're looking for the speed of B right here. So I'm going to just leave it in terms of the speed of B and not worry about the R omega term, which would bring in the angular acceleration of this linkage dB, which we don't really care about. That term is equal to omega AB, which we're not sure about the magnitude, but we know it's pointing in the outward of the page, cross with the relative position vector of A relative to B. That's negative 120 in the I plus a 50 in the J. Again, performing that cross product. If we project in two directions, the x direction as well as the y direction, by dotting both sides with those two vectors, what we're going to get for the, let's start with the y direction, is negative 600 is equal to negative omega AB times 120. From right here, what we see is that omega AB is just equal to 5 radians per second. What about if we look at the I direction? We get the negative of the speed at point B is equal to negative 50 omega AB, and we just found what omega AB was. So the speed of point B is just equal to 250, right? 50 times 5 is 250. That will be millimeters per second. If we go ahead and plug the speed of B, which we just found, as well as the omega AB, into our angular acceleration equation, what we'll get is 250 squared divided by RBD. RBD is just 80 millimeters minus 50 multiplied by omega AB. Omega AB was 5. We're going to square that term and divide it by 120. Okay, what we get for alpha AB here is that we get negative 3.91. That's radian per second squared. What does this negative mean? If we go back to what our assumption was about alpha, we said that alpha AB written as a vector is equal to alpha AB, its magnitude pointing in the k direction. We have what its magnitude is. Its magnitude is 3.91 radian per second squared. Its direction, we take that minus and apply it to the k hat. What that means is that instead of pointing out of the page, we point our thumb into the page, and our fingers will curl in the direction that the alpha is actually traveling in. So that'll be clockwise. Instead of writing this, 3.91 radian per second squared, clockwise is the solution. Let's go ahead and check our answer here. Okay, so we got the answer correct. If we read through the solution here, just to quickly review what we did, we started with the relative acceleration equation. We recognized that point B had simple circular motion. We reviewed that circular motion, and we also made this simplification on the double cross product, giving us a pretty simple equation here. We plugged in what we thought was the angular acceleration of B in terms of the circular motion, the acceleration of B in terms of the circular motion, the angular acceleration of AB, right, which we know was into or out of the page, and the relative position vector we could kind of just read off. Same thing for the omega, and we ended up with a relationship down here. And that relationship was in terms of the speed of B as well as the angular acceleration of AB. We solved for that using the relative velocity equations, and we were able to conclude that our answer was 3.91 radian per second squared clockwise. If you understood this entire video, you'll never have to watch another relative motion equation again, or another relative motion video again. I hope that you got something from this video. Please leave a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.